So welcome everyone to our seminar this afternoon. Our speaker today is Wang from Vanderbilt University. So will tell us about Helton-Howe trace formula on submanifolds. So please.
Okay, thank you for the introduction. Today I'm going to talk about, the main topic is about our recent paper. It's the joint paper with Quanlei Fang and Jingbo Xia. First, let me introduce the Helton-Howe trace formula. So to begin with, it involves this anti-symmetric sum. If you are given a tuple of bounded operators on Hilbert space, you can define this anti-symmetric sum. So this is my secret notation of like understanding this. So first, you can see like this is a generalization of usual commutators, and like if you span it in the first row, you get this thing. So it's like abstraction to commutativity and a generalization of usual commutators. And this anti-symmetric sum is first raised in this paper. Since I'm already on my note, I can just go ahead and show you the paper maybe. So this is the paper I'm talking about. So this is a second paper in a series. In the first in the first paper, the authors considered these normal commutators and build an index formula for them. And this is a generalization for tuples, k tuples of operators. So basically, they consider generalizations of say pseudo-differential operators, algebra of pseudo-differential operators, or Toeplitz operators. And they developed some abstract theory. In general, they consider this so-called crypto-integral algebra of dimension n, which just means you have a collection, self-adjoint collection of operators, and they need to satisfy certain conditions on these commutators belonging to certain Schatten class groups. And then they study this invariant trace of this anti-symmetric sum. And as an example, in the last part of the paper, they give two formulas. Let me show you. Yeah, section 7 examples. So the first example they gave is about pseudo-differential operators. And this is the formula they get. If you have a compact, smooth, n-dimensional manifold M, and this is some collection of pseudo-differential operators, then it satisfies the conditions they gave, and you have this kind of trace formula. And so this is, I'm not an expert on this, but I think this somewhere they mentioned that this is a consequence of the Atiyah single index formula. And another example is the Toeplitz operators, and you have a similar formula here. So I will introduce this in my note. Yeah, so they studied this invariant. So Helton-Howe trace formula. To start with, we are looking at the Bergman space on the unit ball of Cn. So that means you take all the holomorphic functions inside the L2 of Bn with the Lebesgue measure. And the Toeplitz operators are exactly the compression of multiplication operators on the Bergman space. So like you have this decomposition, the Toeplitz operator is on the one corner. And what they prove is if you look at Toeplitz operators with polynomial symbols, not necessarily uh, uh, analytic polynomials, just any polynomial. If you look at polynomial symbols, you have this integration formula for the trace of this anti-symmetric sum. And so that's for the Helton-Howe trace formula, the traditional one. So from a very different perspective, I want to introduce the geometric Alfvén-Douglas conjecture. So it basically says if you have a complex variety in Bn, you could consider the collection of all holomorphic functions on the Bergman space which vanish on this complex variety. So this is what we call a submodule in the sense that this space is invariant under multiplication by like analytic polynomials. So you are considering a module over this ring. So this is a submodule, and correspondingly we have quotient module, which is the orthogonal complement, and also you can think of the quotient. So like this is, if you compare it with a geometry, it should be like very similar. There should be very similar settings. And our studies show that, so intuitively, this submodule is supposed to be relatively large. So it's like, in some sense, it would be very much like the Bergman space itself. And the quotient module is supposed to live on the variety in the sense that in some extremely nice cases, you can prove that this module is up to some error term, it's similar to the weighted Bergman space on your variety. So you can see you can expect this quotient module to carry some geometric information of the variety. And so the you can define Toeplitz operators on submodule, and the quotient module is simply just compress further the multiplication operator on the corresponding spaces. So that's what we call generalized Toeplitz operators on submodule or quotient module. And the geometric Alfvén-Douglas conjecture says, so this is actually a problem. So if you have a variety, you define this submodule, quotient module, and we ask whether this quotient module is P essentially normal for any P greater than the complex dimension of the variety. And this P essential normal, so essentially means if you consider these polynomial symbols, then these generalized Toeplitz operators should commute up to an area of Shelton class, where Shelton P class, where P is greater than this dimension. And like as a consequence, you can also have this. So that's what I mean by submodule be like the whole space, because they have the same property as the whole space. The commutator is in Shelton P, but only for Shelton Q, but only for Q greater than the total dimension. So let's see. So this concerns our another paper, a previous paper. So let me show you directly. So that's our previous paper. We studied the geometric Alfvén-Douglas conjecture under certain assumptions. So this is our assumption. If you have an analytic set in an open neighborhood of the closed unit ball of Cn, and we assume that the variety satisfies these three properties. It intersects boundary transversely. It has no singular point on the boundary, and like it's of pure dimension D. So this pure dimension is not essential. These properties are essential. So like so under these conditions, you see, maybe that's just to go through this. Okay, so so this is a picture in mind. This is unit ball. So your variety could have some some singularity inside the ball, but not on the boundary. And you just define M to be the intersection of this whole analytic set with the ball. And then similarly, you can define as here. So you can define respondingly Rm space, that's the function's definition on M, and the Qm space, that's the orthogonal complement. And you also can define Toeplitz operators on submodule, Toeplitz operator on quotient module. And so this is a list of 2 papers. In the 2 papers, we prove that the geometric Alfvén-Douglas conjecture holds under this assumption. So then once we prove this, then we know that so this QM and RM fit into this framework of the so-called crypto integral operator of dimension n. So then we can ask for a similar formula like this. So this is a little explanation of how we proved this geometric Alfvén-Douglas conjecture, so which we will involve in the proof of the present paper. So essentially, we proved the following. So you define this integral operator. So mu is this weighted volume measure on your variety, and you define this integral operator, which is a positive operator. And essentially, we prove that in the spectral decomposition of this integral operator, it would look like this. There's a spectral gap. So this is the spectrum of this T-mu operator. You have 0 corresponding to kernel of T-mu, which is exactly the Rm space. And you have another part corresponding to its complement, which is our QM space. And what we prove that is that there's a gap in the spectrum. And once you prove there's a gap, you can, you know that the QM projection operator is a smooth functional calculus of this T-mu operator. And using some technique, we can prove like T-mu operator commutes with the multiplication up to some Helton class. I think that's 2D. And using this, we can prove QM projection commutes with MF up to Helton class, the right Helton class. And that would lead to our conclusion here. So this is also our last paper. So as a consequence of this improved bound on the Helton class membership, we are able to prove 2 things. So the first thing is this anti-symmetric sum of generalized Toeplitz operator on submodule. So assuming this hypothesis, this anti-symmetric sum is in the trace class. So it makes sense to ask for the trace for this anti-symmetric sum. And the second thing is about QF. So if your M is greater than the dimension, then actually these anti-symmetric sums are all trace class of zero trace. So if you go larger than the dimension, then the trace formula just give you 0. And I put a remark here, like, of course, it would be more interesting to consider the QF, this anti-symmetric sum with 2D operators in the case of quotient spaces. But in the present, we are not able to prove it. So I think this would be a very interesting like subject of research. If anyone in audience know anything, please talk to me. Okay, so this is our main result of this paper. So we have proved this is in the trace class, and our new conclusion is that we actually have the same trace formula for submodules as in the total space, the total Bergman space. So essentially, we are proving that the trace of the usual Toeplitz operators and the trace of the submodule Toeplitz operators, so they are the same. So like when you look at it, you expect it to be an easy, like very easy, because you have this improved commutativity. So that was what we thought in the beginning, and you actually can prove such results given that the dimension is small. I think using some algebraic techniques, what we can get is if you get d less than 2/3 of the total dimension, then you can just using some very complicated, but it works, like using some complicated algebraic argument to prove this kind of theorem, but we can never, so we are not able to do that for d equals n using a purely algebraic argument, like d less than n. So how do we prove this? So essentially, our approach involves two things. The first, so like abstractly, we are proving this theory. So this, if you have a total space P and you break it into R and Q, so you have these projections. And if you abstractly, you have 2m tuple of pairwise commuting operators, and you define these compression operators. And if you know that the big one, the compression on big one is trace class, and we need some commutativity here. So that's just generalization of what we know on the quotient space. And what we do is a finite rank approximation. So essentially, if you have a sequence of positive finite rank operators that approximates, so I should also add, of course, Q minus AM norm tend to 0. So so if you have like an estimate on the norm and an estimate on the p norm of the commutator, then we can conclude that the trace of these two anti-symmetric sums are the same. So this is the first thing we prove. And the second thing is just to prove like what we are working on fits into this framework, which means if you replace P for the projection of the Bergman space, Q for the projection of the quotient module, and R for projection to submodule. And these are multiplication operators with polynomial symbols. You get all these conditions you want. And so here is a little detailed explanation. So for part 1, which is our framework here, so I'm using the old notation. So this is what we have, and I will show you some algebraic techniques. So you are looking at this the difference of antisymmetric sum, and if you write everything out, so like write like TF as P, MF, P, and R would be like so like if you are taking difference, so at each space you have somewhere you get P minus R instead of P or R, and that would improve your commutator membership, and basically that's the idea. So algebraically you have this expression, and each of these xi is either R or Q, but not all R or not R or RQ. Sorry, I think this one is not. So Q, we need to treat Q separately, but so this is the case. And so once we are written in this form, we need some little trick. So this is an example of what we are doing. So so you have, say you have R in the first 3 places, because these 2 operators commute, and because you are taking sum on all permutations, you can replace this R by -1 minus R, because when you put 1 and take antisymmetric sum, this just cancels. And if you look at this part, is actually the same as the commutator multiplies 1 minus R, because on the reversed part, you like R times 1 minus R just cancels. So that's how we get the commutators inside in the estimate. And essentially, how do we prove this trace is 0? So you have like a collection of these operators. So essentially, we are proving if these 2 ends, so they might be R, might be Q. If one is R, one is Q, then we want to prove this is just a 0 trace. So equivalent means the difference is a trace class and of 0 trace. So if the 2 sides are different, you get 0. And if the 2 sides are the same, so you can, we are proving you are able to move this part to the other side. And now the order changes, and like combining the sign here, you get like this, and this whole sum would have 0 trace. So that's the algebraic part. And this is an important lemma that appears in Helton-Howe's paper, which is improved result. Like we know, like in classic theory, if A is in trace class and B is arbitrary operator, this would have 0 trace. So this is an improved version. If you have a self-adjoint operator and another one is compact operator, if you know the commutator is in trace class, then the trace is 0. Yeah, I think this is well researched, like studying this problem. One of my questions, like, is it possible to generalize this lemma to like anti-symmetric sums? So I don't know the answer. Probably someone in the audience might have a thought on this. I think it's an interesting question. So this is the first ingredient we put in our proof. The second part is dilation. So remember in our setting, we used finite rank operator approximation. But one problem is that your operator is not necessarily a projection. And if you replace, so basic idea is just to replace Q with AM operator and do approximation. But the problem is that AM is not a projection. So when you do this argument, you will encounter this property here. So like you are essentially using the property that you are looking at a projection. So that's another abstraction we need to tackle. So what we do is just do dilation. So this is like a classic dilation like matrix. So we put this operator here, we get dilation, and basically we dilate everything we are looking at, and we prove like the resulting trace is the same with the previous one, and etc. So that's another ingredient we put in. And the second part of the proof involves proving that your operators fit into this framework. Essentially, we want to prove this kind of estimate. And so let me show you what's our candidate for the finite rank approximation. So basically, we know that the projection is the function, a smooth functional calculus of the T-mu operators. So we'll go ahead to look for a finite rank approximation for this T-mu operator, which I say called T lambda mu. And this is a rough picture. So basically this is the unit ball. This is a smaller ball with like slightly smaller radius. And so you have this measure mu on the variety. And so this is our T lambda mu. So first you have to like replace this mu continuous measure by discrete measure, which we can. So we can replace mu by some discrete measure. Like it's sort of like an atomic decomposition on the variety. And so when you then you just restrict the measure to this inside part, and this will give this T lambda mu will give you a finite rank operator with the right approximation. And then we use some like Fourier functional calculus, like inverse theorem things, kind of things to get an estimate on Q. So that's and also, right, so this is how we prove for this finite, this T lambda mu has the right approximation. So it's called the norm rank estimate. Basically, it depends on this theorem. Sorry. So if you can decompose your if you can decompose your targeting operator into a series, and for each part you have a finite rank, so you know that the rank of each part has an estimate and has a rank estimate and the norm estimate, then you know that this series, the sum would have this CP plus membership. So CP plus is another operator ideal, is slightly larger than CP. So, I don't. So that's my talk. Any questions?
Okay, thank you. Do we have any questions or comments? So E, I have a question about your result. So using your result, what's the difficulty in understanding the Q operator?
What's the difficulty of understanding the Q?
I mean,
So
your main result computes the trace of, the Helton-Howe trace of this RFs. So how about for QFs? You said it is a difficult. You think you have some challenge or difficulty. So what is?
I think so. The thing is, probably we don't know enough like geometry to proceed. The thing is, in the whole space, you have this basis. So like on Bergman space, because you are looking at these polynomial symbols, you can just look at TZR for instance. And once you establish a trace formula for these spaces, these monomials, you can go ahead and prove the general trace formula, but there's no such thing for subvarieties. Maybe, I don't know. Do you have any thoughts on how to obtain a result like formula for this one?
So maybe we can talk about it afterwards. So one idea is if we can identify the K-homology class, and you know also this Helton-Howe trace is a kind of top degree component of this cons chain character for cyclic cyclic cohomology of the K-homology. Then
okay.
So if we know what is the variety we're working with and what is the exact geometric identification of the K-homology class, then maybe there's a chance to identify this cyclic cocycle of as the chain character of the K-homology class.
Yeah, that would be an interesting thing.
So E's formula, I think, is true on the nose. It's more than just true at the cohomological level.
Sorry, on the what?
Oh, I'm just saying that your formula, it gives more information than just, a formula like at the cohomological level.
Oh.
Like
yeah,
given by computing the chain character. But there is a connection there.
Yeah, maybe we can talk about it later.
So another question here is, you have considered polynomials for F. So how about the more general functions? Like
I think we wrote for polynomials, and later I realized, so I can show you, like in the general theory, they consider polynomial, but I just realized that for their example, they are actually doing smooth functions. So if this formula is true for smooth function, I think we can do the same. Like we can have this formula for submodules for smooth symbols. That would be true. Is that what you're asking for?
Yeah, I was asking about that. Yeah.
Okay.
So, okay, sorry. Are there any other questions besides my question? Or comments? Okay, let's thank you again for a nice talk.
Oh.